This segment of the class is primarily all about sensors. A sensor is any kind of a device that converts a physical property into an electrical property. Physical properties might be things like light intensity, or the position or speed of a motor shaft, an amount of heat or temperature, or even the presence or strength of an electrical field. This isn't a comprehensive list. There are many other physical properties that we can sense using sensors. Electrical properties are things like voltage or current. The benefit of a sensor is that it allows our controller, which is an electrical kind of a controller, to obtain information about the physical properties. In a robotic system, there are two primary kinds of information that a sensor would be used to give us. The first use is perhaps the more commonly understood use, which is to give our robot information about its environment. In other words, to give the robot information about what is happening around it. The robot might have a sensor that detects light intensity to determine the position of the sun at any given time. Or maybe our robot will have a temperature sensor to give it information about the current season or the current weather. The second primary use of a sensor in robotics is to give the robot information about its own self. This is a use of sensors that we've already seen in the second part of this class on control. In that part of class, we used a sensor to do feedback position control. If you remember, in order to do feedback position control, the robot needed to have a sensor that could inform it of the current location or the current position of its own joints. In order to effectively use sensors in our robotic systems, we need to be able to select appropriate sensors. We need to know how to read sensor data using our robotic controller. And finally, we need to know how to convert data, that is, the raw value that we read from the sensor, into information, that is, some data in a form that we can use in our robotic control. In this first set of videos, we're going to be looking specifically at how to select appropriate sensors. One of the most important pieces of information you need to know in order to select appropriate sensors is you need to have a wide knowledge of the different kinds of sensors that are available. In this set of videos, we're going to go through some of the most common and useful sensors that are available for use in robotic systems. In this first set of videos, we'll be looking at the wide variety of sensor types that are available. We will look at resistive sensors. Those are sensors that detect a physical property by relating it to a changing resistance. We'll also look at capacitive sensors. Capacitive sensors detect a physical property by relating the physical property to capacitance. We will also look at inductive and magnetic sensors, optical sensors, piezoelectric sensors, and finally acoustic sensors. We won't spend more than 5 minutes on each of these different kinds of sensors. The idea is to give you a wide view of the different kinds of sensors you might want to use for different kinds of applications. If you have some idea of the kind of sensor you want to use for a given application, you can then look in more deeply into that particular kind of sensor. For now, we'll just look at these sensors on a surface level view. In this video, we're going to be taking a look at resistive sensors. Resistive sensors are resistors whose resistance is affected by a particular physical quantity. In this way, the variable resistor is able to convert a non-electrical property input into an electrical property output. Resistive sensors can be used to measure many different kinds of physical quantities, some of them unexpected. We can measure temperature, light, deformation, and even magnetic field strength by using a resistive kind of a sensor. The reason why resistance can be used to measure so many different kinds of properties is because resistance of a material depends on a lot of different physical properties of the resistive material. Resistance depends on shape, size, material properties, and even the environment of the resistive material. Do you remember how we calculate the resistance of a resistive piece of material? In this case, the resistance of a rod. Resistance is equal to a material and, in some cases, also environmental property called resistivity times the length of the rod, here's the length in this picture, divided by the cross-sectional area, right there. Because resistance is equal to the product of resistivity and the length divided by area, we can actually make different kinds of resistive sensors that work by changing any one of these three quantities, the resistivity, the length, or the area. We have different names for each of the different kinds of sensors that works by changing these different properties. The one that's most common and that we've already seen is potentiometric sensors. We've already used a potentiometer to measure the displacement of our little slide potentiometers. Potentiometers work by changing the length part of this equation. By moving a wiper connected to a contact along the resistive material, we can effectively change the length of the resistive material. Another common sensor that you may have used before is a strain gauge. A strain gauge works by changing the cross-sectional area of the resistive material. When we pull or push on this resistive material in order to place it in strain, the cross-sectional area will change as the part is stretched or compressed, and that can be measured as a change in resistance due to the changing cross-sectional area. Other resistive sensors that are less common are shown over here. Piezoresistive, magnetoresistive, thermoresistive, and optoresistive sensors all work by affecting a change in the resistivity property of the material. We will look at one or two of these different kinds of sensors in this video. Take a moment to recall what we learned about how a potentiometer works. With two connection leads, shown here as A and B, at either end of a single resistive material, and a wiper which can turn and change the effective length between either one of the two leads and the wiper. Most of the time when we're using a potentiometer in robotics, we're generally using the potentiometer as a voltage divider. In other words, we want the voltage coming through pin 2, the wiper, to vary depending upon the position of the wiper. However, note that there is a different way to hook up the potentiometer. When we use the potentiometer to control the voltage in our power circuit, we hook up the potentiometer differently as what's called a rheostat, or just a variable resistor. Now, let's take a look at a different kind of resistive sensor, a piezoresistive sensor. A piezoresistive material is one that changes its resistivity property when it is deformed. In fact, the word piezo, which we will see cropping up again when we talk about different kinds of sensors such as piezoelectric sensors, means to squeeze or press. Piezo sensors of all different kinds are sensors that change an electrical property when they are squeezed or pressed or deformed. One kind of material that works as a piezoresistive sensor is called an elastomer. An elastomer is an elastic material that has conductive particles embedded within it. When this material is compressed, as is shown on the left here, the conductive particles are close together, and so the resistivity is low. And when the resistivity is low, the resistance of the material is also low. When the material is released from its compression or even stretched, then the conductive particles become far apart, and so the resistivity of the material becomes higher. So these kinds of sensors can be used to detect a force or a pressure. For example, if you had a robotic hand and wanted to detect when the robotic hand had come into contact with an object and was pressing on it, you might use elastomers on the fingertips of the robotic hand. Or if you need to detect when a robotic gripper has grabbed an object with a certain force, an elastomer might be used in the gripper to convert the force of pressure exerted by the gripper on the object into a resistance that can be detected as a changing voltage. Also note that besides elastomers, silicon also exhibits piezoresistivity. In some cases, silicon might be a better material to use than elastomers. In the next set of videos, we'll be looking at different kinds of errors that sensors can exhibit, and we'll compare these different kinds of sensors according to the different amounts of error that they exhibit. But for now, note that elastomers and silicon are both options for piezoresistive sensors. Resistive sensors can also be used to measure temperature. In fact, no matter what you're trying to measure with a resistive sensor, you will always have an effect of changing resistance based on the temperature. So you need to be careful if temperature is not what you're trying to measure with your resistive sensor, to note that the sensor will behave differently if it's hot outside than it will if it's cold outside, if your robot is operating outside. Thermoresistivity is a property of a material that says that that material changes its resistance in response to a change in temperature. There are two materials that do this: metals and semiconductors. If we have a thermoresistive sensor that's made of metal, it will be called a resistance thermometer. If our thermoresistive sensor is made of a semiconductor material, then it will be called a thermistor. In general, thermistors are cheaper devices and have higher error, and they're less reliable, while resistance thermometers are generally much more expensive devices, and they're more accurate and more linear, higher quality sensors in general. Finally, resistive sensors can also be used to measure light intensity. However, I'll go over this in more detail when we get to the optical part of these videos. Now, let's take a look at some capacitive sensors. Capacitive sensors are sensors that work by varying the electrical property of capacitance. Remember that capacitance means the ability of a material to store some electric charge. In order to use capacitance to measure a physical property, our sensor still needs to have some kind of an electrical output. We usually want to measure voltage. Is there a relationship between capacitance and voltage? In fact, capacitance is nicely related to voltage. The amount of charge stored in a capacitor is equal to the capacitance times the voltage. So if we have some physical properties that vary the capacitance in a capacitor, we can measure the change in that capacitance by measuring the voltage across the two plates. So here's a summary of how capacitive sensors work. We have some physical property that changes the capacitance of a capacitor, and we measure the voltage across the two plates in order to determine the capacitance and then back out the value of the physical property. So what kinds of physical properties are related to capacitance of a capacitor? When we were looking at resistive sensors, we started by writing out the equation that determines the amount of resistance in a resistive material. We can do the same thing for capacitive sensors. Capacitance is equal to permittivity. That is a material property that is similar to resistivity in a resistor. Similar to resistivity, the permittivity depends both on the properties of the capacitive material itself and also on some environmental properties. The capacitance is also related to the cross-sectional area, which is overlapping of the two plates, and the distance between the plates. So if we can relate some physical property that we want to measure to the cross-sectional area, or the distance between the plates, or the permittivity, then we can measure that physical property by measuring the voltage through the capacitance. Capacitive sensors can be easily used to measure small amounts of displacement. I'm showing here 3 ways that a capacitive sensor could be used to measure displacement. One way, shown in part A of this figure, is to change the distance between the two plates. Although changing the distance between the two plates in order to measure displacement only allows us to measure a very small displacement, this approach is very accurate. We can measure small displacements very accurately by causing the displacement to change the distance between the two plates of the capacitor. Another way to measure displacement with a capacitive setup is to change the amount of area that is overlapping between the two plates. This is shown in part B of this diagram. As the top plate slides off of the bottom plate, the amount of area that is overlapping between the two plates becomes smaller. That in turn changes the capacitance, and we can measure the voltage change. The third diagram shows a rod sliding out of a sheath. As the rod slides out of its sheath, the overlapping area between the sheath and the rod changes, becomes smaller, and so we can measure the changing capacitance as the rod slides out of its sheath. One of the drawbacks of this kind of capacitive measurement is that we need to have a physical electrical contact attached to both sides of these plates. In other words, in figure A here, we would need a wire to be physically connected to the top plate and to the bottom plate in order to measure this displacement. However, there's a different way that we can make a capacitive sensor that allows us to not have to have a physical wire attached to both plates. The kind of a capacitive sensor that doesn't require us to have a wire attached to both the top and the bottom plate is called a differential capacitive displacement sensor. Here's a diagram showing how this kind of a sensor works. Here we have 2 plates, one on the left, one on the right, and each of those are attached to a wire. We also have a plate in the center that is grounded. The plate on the top does not have a wire attached to it at all. Instead, the electrons are able to jump from one of the bottom plates onto the top plate, travel through the top plate, and then jump back down into the grounded plate. So this device makes a complete capacitor even though we only have an electrical connection to the bottom plates, not to the top plate. Can you think of why this kind of a setup would be very useful to us? For one thing, having more electrical connections gives us more opportunity for the device to fail, especially if the moving part, the top plate, has to have an electrical connection. It's always difficult to have a physical electrical connection to a part that's moving. However, there's another benefit that is not immediately obvious to this kind of a setup. That is that the top plate does not necessarily have to be a metallic material. It has to be a conductive material, but it doesn't have to be metal. In fact, it could be something like a person's finger. We're all probably familiar with capacitive touch screens that are able to detect the position of our finger when it touches a screen. How can it do that, given that our finger does not have an electrical contact to it? The differential capacitive displacement sensor explains how this is possible. The electrons in the bottom plates, which are attached to the device, can jump off of that plate onto a nearby finger and then back down into a grounded strip. And in that way we can detect the change in voltage as the finger moves across the screen. Let's take a look at just one more type of capacitive sensor that is often used in robotics. That is the capacitive accelerometer. A capacitive accelerometer is made by creating a structure which consists of a thin beam on the bottom and a thick beam on the top. Electrodes, that is, plates of the capacitor, are placed facing each other on these two beams. Gravity pulls down on the bottom beam and the top beam and causes deflection in these two beams. However, the bottom beam is deflected much more than the top beam because the bottom beam is much thinner than the top beam. And so, as the device changes its angle of tilt, the angle of pull from gravity changes its direction. When the device is upright, as shown in this picture, the bottom beam is pulled down much farther than the top beam, and the distance between the plates becomes greater. However, if this device is upside down, then the green beam will instead be pulled closer to the top blue beam, and the two electrodes will become closer together. The distance between the plates changes its capacitance, which in turn changes the voltage between the two plates. We can measure this changing voltage, and so we can back out information about the angle of tilt of this two-beam setup. Now, note that this entire device is made to be very small, so that the entire device can be embedded inside of a single chip. Unfortunately, because this device is so small, the capacitance is also very small, and so it's hard to detect. Usually when these devices are made, they're made more like the picture shown here, with many beams interleaved between each other. The entire device can still be made very small, but the capacitance will be greater and easier to measure. There is an entire field of study devoted to trying to figure out how to build devices like these that are very small. And this field of study is called MEMS. MEMS stands for Micro Electromechanical Systems. These devices are called micro-electromechanical systems because they're microscopic devices that include both electrical components and mechanical components. MEMS is a field that is highly related to robotics that shows great promise for expansion in the future, especially as we become more and more interested in embedding sensors into everyday devices. Inductive and magnetic sensors are sensors that relate physical properties to electrical inductance and the changing magnetic fields. There are many different kinds of sensors that can be made with these properties, but here I'm just going to focus on two different kinds of sensors that are the most common in robotic kinds of applications. The most common kind of inductive and magnetic sensors used in robotic applications are displacement sensors. Specifically, the kind of displacement sensor we usually make with inductance and magnetics is proximity sensors. Proximity sensors are displacement sensors that aren't necessarily used to measure the actual distance between two objects, but simply to trigger when one object comes near to another object. One kind of proximity sensor is called a reed switch. A reed switch is a sensor that has a glass housing. It's not always glass, but it often is made of glass, with two bent pieces of metal inside of the housing. Now, when a magnet approaches the housing, the magnet exerts a force on the two reeds, these filaments of metal inside the housing, and it causes them to contact each other, thus closing the switch. This kind of a sensor can also be made to be activated not by a magnet, but by a coil of wire. The other type of inductive sensor that's common in robotic applications is a type of sensor that's called either a resolver or a synchro. These two types of sensors are very similar to each other, and they're both used to measure rotational position and velocity. Unlike potentiometers, resolvers and synchros can measure rotational angles for a full 2 pi radians, or 360 degrees of rotation. You don't need to know these equations that are shown here on the page, but I've included them to remind you about how magnetic flux works. I've shown in this picture a single coil of wire with some magnetic flux lines going through the coil. As the coil of wire turns, the angle between the plane of the wire and the magnetic flux lines changes. This changing direction of the magnetic flux through the coil of wire induces a voltage across the coil of wire. In this equation, omega is the rotational velocity of the coil of wire. So, if we want to find out the rotational velocity of the coil of wire, we can do that by measuring the voltage across this one coil. Here's how we can use this property to our advantage. We will attach two coils of wire to the stator of the motor, and we will attach a rotating coil to the rotor. Now, if we put an alternating current through the two stationary coils, these two coils will produce magnetic flux. Then, as the rotating coil rotates, as the motor rotates, because this coil is attached to the rotor, the voltage across this coil is going to change. And we know that the voltage across this coil will be proportional to the speed at which this single coil is rotating. that allows us to measure the speed of the motor's rotation. We can use that measurement to do speed control of a motor, or if we're keeping track of time, we can then also calculate the position of the motor and use that measurement in our feedback position control. Now, let's take a look at some optical sensors. Optical sensors are based upon the property of optoresistivity. Optoresistive sensors are made of materials that change their resistivity in response to the intensity of light, and this effect is called the photoresistive effect. Some natural materials that do this are cadmium sulfide and cadmium selenide. These sensors that are made out of these materials are called light-dependent sensors, sometimes abbreviated LDR, or they might be called photoresistors, or they might also simply be called photocells. You've probably seen sensors that look like this before, and if not, we'll probably be using these in class in our labs. With an optoresistive sensor, when light falls on a photoresistive material, one of those materials that we talked about in the last slide, free charge carriers are generated by the material. If you've learned about semiconductors before, you would recognize two different kinds of free charge carriers, which we refer to as electrons and holes. These free charge carriers are basically particles of material that have an unbalanced electrical charge. They either have more electrons than they should, or they have fewer electrons than they should. Those are what we refer to as holes. So, as the intensity of light increases, the number of free charge carriers in the material increases, and that causes the resistance to decrease, because when there are more free charge carriers, electricity is more easily able to move through the material. And so optoresistive sensors are used in the same way that other resistive sensors are used. You'll notice that on the picture of this optoresistive sensor, there are two leads coming out of it. The two leads are very similar to the two leads coming out of a resistor. The difference here is that the resistance across these two leads changes based on the intensity of light. And so you can use an optoresistive sensor in the same way that you use a potentiometer or any other variable resistor. Now, optoresistive sensors are useful for measuring the intensity of light, but we can combine optoresistive sensors in different kinds of combinations to measure things other than the intensity of light. Let me show you one example that's particularly useful for us as robotics engineers. Here I'm showing you a motor that I pulled off of a robotic device to show you a little bit about this device that's attached to the back of the motor. This device is called an optical encoder, and I've removed the casing so that I can show you what the optical encoder looks like inside of it. An optical encoder is an optical sensor that's used to measure rotational position and rotational velocity. If we look inside of this encoder, you'll notice that there is a little disc right here. It's a plastic disc, and if we were able to zoom in much farther than we're able to right now, we would see that there are little black marks positioned all in a circle around this plastic disc. The plastic disc is attached physically to the shaft of the motor, so you can see that if I turn the shaft of the motor with my fingers, this plastic disc also rotates. Now, the plastic disc is positioned so that it is right in between these two brown plastic parts, which you can see right there, this brown plastic part, there's a top and a bottom part of this plastic. Now, in the bottom part of this plastic, there is an LED pointing up so that it shines through the clear plastic disc that rotates with the shaft. As I rotate the shaft and the clear plastic disc rotates, these little lines that are in the disc alternate. Now, if I turn the camera at just the right angle, you can kind of see, there we go, right here, that these marks on the disc alternate dark black lines and clear lines. As the shaft rotates, the light shines through the clear lines and the light does not shine through the black opaque lines. Now, in the top of this brown plastic piece up here, there is a light sensor like a photocell that is detecting the pattern of bright and dark pulses that it gets as this disc rotates and alternates its clear and opaque lines. When you buy a motor with an encoder on it, the encoder includes a specification that tells its number of lines. You might find an encoder with something like 512 lines. That number tells us how many of these clear lines are included around the entire circumference of the clear disc. And that tells us the resolution of the sensor. In other words, if the encoder has 512 clear lines, we can detect an angle change of 360 degrees divided by 512. The clear disc that you saw in that video looks like the picture shown here. It has two tracks, one with equally spaced slits or clear lines, and one track with only one single slit on it. This is done so that we can detect the position around the circle, and also we can detect when one complete revolution has been made. This type of optical encoder is called an incremental optical encoder because in order to determine the rotation, we have to count up the number of slits that have passed by counting up the number of pulses of light received by the optical sensor. Another type of optical encoder is called an absolute optical encoder. This type of encoder has several concentric rings of slits, and each position around the disc gives a unique bit string. This type of encoder allows us to keep track of what the position of the shaft of the motor is, even if power is removed and then applied again. Whereas an optical encoder can only tell its position by counting up slits while the shaft is actively rotating, an absolute optical encoder can tell its position at any time because every position gives a unique string of bits. Piezoelectric sensors are similar to capacitive sensors in that we're using the electrical property of capacitance to measure a physical property. Piezoelectricity is a property in which a material develops a charge in response to a physical deformation. We take these materials and make capacitors out of them so that we can get a voltage in response to deformation. In other words, the deformation, for example, bending or compression or stretching, causes a charge in the capacitor. Because the charge is changing, we can measure the change in deformation by measuring the change in voltage across the two plates of the capacitor. So, why does piezoelectricity occur in the first place? This happens because of the crystalline structure of some materials. Crystals are units of material that are symmetric, so that the positive and the negative charges are equally distributed and they're all lined up. Because the charges are all symmetric, the center of gravity, or the center of mass of the positive charges, is in the same location as the center of gravity of the negative charges. However, when we press on or deform the crystal, the charges move their positions so that the center of gravity of the positive charges is no longer the same as the center of gravity of the negative charges. As a result, the whole piezoelectric material develops an imbalance in its charge, so that, for example, the top of the material has more of a negative charge and the bottom of the material has more of a positive charge. If this material is connected to a wire, charges in the wire will rush to equalize the charge imbalance in the material. And this rush of charges to equalize the imbalance gives us a remaining charge on the piezoelectric material when the wire is removed. So, in other words, when deformed, a piezoelectric material becomes polarized. It has an imbalance in the location of its charges. Now, note that this effect is actually reversible. In other words, if you put a voltage across a piezoelectric material, it will deform. Just as if you deform a piezoelectric material, the voltage will change. Because of this property, piezoelectric materials can be used either as sensors or as actuators. So, since a piezoelectric material occurs because of the crystalline structure, let's take a look at what kinds of materials work for making piezoelectric sensors. Curiously enough, there are some natural materials that exhibit a piezoelectric property. One of these is quartz. Quartz has a piezoelectric property because it's a natural crystal. But it doesn't give us very much of a piezoelectric effect, only about 2 picocoulombs per Newton. Now note the units on this piezoelectric effect. It's stated as charge divided by force. That's because a piezoelectric material works by developing a charge in response to deformation. Perhaps even more curiously, human bone also exhibits a piezoelectric property, as well as tendons. Does this perhaps serve as a biological force sensor? But once again, this material also doesn't give us a very large piezoelectric effect. One material that works to give us a sufficiently large effect to be used as a sensor is a crystallized ceramic. The way we make ceramic piezo sensors is by taking the ceramic up to a temperature that's called its Curie temperature. At this temperature, the material's charges can move around. We then expose the ceramic to an electric field so that the charges all line up into a crystalline structure. We then cool the ceramic back down so that the charges are no longer mobile. And now the crystalline structure of the charges will be maintained. Using crystallized ceramic has a benefit over quartz in that its piezoelectric effect is much larger. Of course, if the ceramic gets heated above its Curie temperature again, it will lose its piezoelectric effect. But it should also be noted that the crystallized ceramic will lose its piezoelectric effect over time regardless. We can also make piezoelectric materials out of polymers. Polymer piezoelectrics don't give as big of an effect as the crystallized ceramics, but it has the benefit that it can be deposited on the top of a silicon chip so that we can make an integrated circuit sensor like a MEMS device that we were talking about earlier. Now, these kinds of sensors can't be used at as high temperatures as the ceramics, since the Curie temperature of a polymer is only about 125 degrees Celsius. But since the polymer melts at 150 anyways, that's generally not a big deal as long as the polymer is a sufficient material for your application. Now, piezoelectric sensors are often used as acoustic sensors, and I'm showing here a diagram of how this works. What we do is we place two plates with a piezoelectric material in between the two plates, and this top plate is placed in contact with the material through which the sound flows, for example, air or water. Now, as the sound waves propagate through the material and strike the plate, a vibration is set up. As this top plate vibrates in and out, the piezoelectric material is compressed and expanded. The compression and expansion of the piezoelectric material causes the charge to change, which changes the voltage, and in that way we can detect the sound waves striking the top plate. Now, the purpose of detecting sound for a robotic application might be something like sound intensity, but more frequently, what we're measuring is something called time of flight. Time of flight is the amount of time that it takes for a pulse of sound to leave our robot, bounce off of an object, and then come back and be detected. An ultrasonic rangefinder is a common sensor that uses the time of flight approach to produce a pulse of sound, start timing, wait until an echo is received back and detected by our piezoelectric sensor, and then stop the timing. So how can we relate distance to time of flight? The time of flight depends on the propagating medium in this way. We have that the distance to the object is equal to the speed of sound times the time to hear the echo. The speed of sound depends upon what the sound is traveling through, whether it's, say, air or water. You can usually get close enough by simply looking up the speed of sound in air or the speed of sound in water, depending upon your application. But you can also calculate it given the equation shown here, using the modulus of elasticity of the medium, the air or the water, and the specific mass. You should also note that the speed of sound in air does depend somewhat on the temperature, since the temperature affects the specific mass. This equation gives an approximation for the velocity of sound in air based upon the temperature in degrees Celsius. Note that since we have sensors to measure the temperature of the robot's environment, if we needed to be very accurate with our time of flight calculation, we could use the combination of sensors in order to calculate the velocity of sound and then calculate the distance to an object given time of flight.